This one is similar. As before, you are given 3 of the factors and you have to find the 4th. Again, we are using a polar stereographic chart. The aircraft position is at 28 south, 118 east. The true track is 042 and the grid track is 133. What is the datum meridian? What is the convergence? Grid track is 133. True track is 042. That's a difference of 91 degrees. True is least, so the convergence is 91 east. Is the aircraft east or west of the datum? We're in the southern hemisphere. With easterly convergence, the aircraft must be east of the datum. If the aircraft is 91 degrees east of the datum and the aircraft is at longitude 118 degrees east, where is the datum? The datum longitude is 027 east. Again, we recommend that you apply the rules, as just shown. It's usually simpler. However, here is the diagram. The aircraft is at 118 east. True north is the direction away from the South Pole. Plot a track of 042 true from the aircraft. The grid track is 133. This gives you the direction of the grid. Parallel the grid through the South Pole. This gives you the datum meridian. Now we'll do one using a Lambert's chart. The only difference to remember is that chart convergence is no longer simply change of longitude between the aircraft and the datum. You have to multiply the change of longitude by the sign of the parallel of origin of the chart. The aircraft position is 50 south, 178 east. The parallel of origin is 56 south, and its sign is 0.82. The grid track is 192 and the true track is 211. What is the datum meridian? So, we need to find the change of longitude between the aircraft position, which we know, and the datum, which we don't. So, the first question is, what is the convergence? It's the difference between grid and true track. In this case, it is 19 degrees, and it must be west, because true is the bigger number. What change of longitude does this represent? The change of longitude, multiplied by 0.82, gives us 19 degrees. Divide 19 by 0.82 to get 23 degrees longitude change. Which way? Back to the usual diagram. The convergence is west, so the aircraft must be west of the datum. This means that the datum is east of the aircraft. The aircraft meridian is 178 east. The datum must be another 23 degrees east. This comes to longitude 201 east. Take it away from 360 to get 159 west. Here's the diagram solution. Again, you'll probably find applying the rules easier. Plot the aircraft position at 50 south, 178 east. This gives us true north. Draw a true track of 211. The grid track is 192, so we can plot grid north. And you can either parallel the dotted line to get the datum, or use the fact that there are 23 degrees of longitude between the aircraft and the datum. Some questions may provide you with a grid chart as an annex. In this case, you may be expected to solve them by plotting, not calculation. Here is an example. Assume a North Polar stereographic chart whose grid is aligned with the Greenwich meridian. An aircraft then flies from the North Geographic Pole for a distance of 480 nautical miles along the 110 degrees east meridian, then follows a grid track of 154 degrees for a distance of 300 nautical miles. What is the aircraft's final position? The possible answers were 78:45 north, 87 east, 80 north, 80 east, 79:15 north, 74 east, and 70:15 north, 80 east. This one is most easily solved simply by drawing it out. Any calculation would be complicated and time-consuming. Using the scale given on the chart, first draw a line 480 nautical miles long out from the North Pole along the 110 east meridian. Using a protractor against grid north, plot in a track of 154 for a distance of 300 nautical miles. Then, by inspection of the four answers, only one could possibly be correct. All that the examiner is trying to establish is that you realize that grid north is the same direction all over the chart. Let's summarize this lesson. It is the third of 3 lessons on grid navigation. We started by reminding ourselves about convergence. We looked at a polar grid chart and a route which involved a large change of longitude in a short distance. As we travelled along the track, the true track changed from 020 to 160. But the grid track remained 090. At every stage, the difference was the amount of convergence, which was directly related to the change of longitude between the aircraft and the datum. We did a practical exercise on relating aircraft longitude and datum to convergence, true and grid, and we noted that in the northern hemisphere, it is helpful to draw the datum meridian at the 6 o'clock position, because north is the direction that runs into the North Pole. However, in the southern hemisphere, we need the datum meridian at the 12 o'clock position, because north is the direction that runs out of the South Pole. We then looked at typical exam questions. In most of them, there are 4 factors: the datum longitude, the aircraft longitude, the grid track, and the true track. The question will normally give you 3 of them, and you have to find the 4th. The best way to solve most of these is simply to apply the rules. Don't forget that, if it's a Lambert's chart, you have to apply the sign of the parallel of origin to obtain the convergence from the change of longitude. A diagram may help you to visualize the situation and aid your understanding. Some problems require a graphical solution. And remember, always, that a straight line track cannot change grid direction. This concludes the lessons on grid navigation. Whilst many modern airliners with flight management systems can cope with polar routes without the need for a grid, it is still necessary in older aircraft for high latitude flying.